Example 2.4.3a. Determine the line voltages in the balanced Y-connected generator shown in figure 11. Draw a phasor diagram of the voltages. Assuming that the load is balanced, determine the phasor line and phase currents if the current drawn in phase A is 10 at angle negative 20 degrees amps. So figure 11 was a Y-connected generator with a neutral. Looks something like this. We've got 3 voltage sources that are all connected together to form this Y shape. We label this one VAN, which is the voltage measured from point A to point N, so it's the voltage across the terminals of that generator right there. We've got VBN, so this point here is point B, and then we've got plus minus VCN right there. So that point right there is C. In the figure, VAN was labeled as 120 at angle 0 degrees volts. And then this is an ABC phase sequence, so VBN is at 120 at angle negative 120. VCN is at 120 at positive 120. So we've got a phase voltage equals 120 degrees ABC sequence, and we've got we were told that the current drawn in phase A is equal to 10 angle negative 20 degrees amps. So this is our givens for the problem. We're asked to determine the voltages on the balanced Y. So if we look at that, this is a 3-phase system, so there's 6 different voltages here at the source. There's VAN, VBN, VCN. And these are called phase voltages, and they're across the phases of the voltage source. And now we also have VAB, VBC, and VCA. These are called line voltages. That's the voltage measured from here to here, the voltage measured from here to here, and the voltage measured from here to here. So these are called the phase voltages that we have. So 6 voltages we have to solve for. We're then asked to draw the phasor diagram. And then we have to determine the phasor line and phase currents given this. And so in the Y system, the line and the phase currents are the same, and so we just need to find IA, IB, and IC if we know what phase did they tell us that was? Phase A. I phase A is equals to 10 at angle negative 20. So now that we've got the problem statement, we'll begin solving it. The solution is just that given in the problem statement, we knew that VAN is equal to 120 at angle 0 degrees. VBN was equal to 120 at angle negative 120 degrees. And finally, VCN is equal to 120 at plus 120 degrees volts. So those are the 3 phase voltages that we have for this Y-connected generator. We know that the relationship between V line and V phase in a Y system is that we multiply by the root 3 at angle 30 degrees. So a line voltage is radical 3 times larger than a phase voltage, and it also leads the phase voltage by 30 degrees. So we've got 3 of those. VAB is going to be equal to root 3 at an angle of 30 degrees times VAN. And so that's root 3 at angle 30 times 120 at angle 0 degrees. And that's going to give me 207.85 at an angle of 30 degrees volts. VBC is going to be equal to root 30 at angle 30 degrees times VBN, and that's going to be equal to radical 3 at angle 30 times 120 at angle negative 120. That's going to give me 207.85 volts at an angle of negative 90 degrees volts. Take a minute to pause. Just like the phase voltages are 120 degrees out of phase with one another, the line voltages are also 120 degrees out of phase. 30 and 90, that's 120 degrees phase separation. So I could also use that to determine the remaining line voltages, and that's going to give me the final one. VCA is just going to be equal to VAB times 1 at, not at radical, at angle 120, because the C phase leads the C leads A by 120. So that's going to give me 207.85 at an angle of 30 degrees times 1 at angle 120. So that's going to give me 207.85 at an angle of 30 plus 120 is 150 degrees volts. So now I've got my line voltages and my phase voltages. So I have to draw a phasor diagram of those. So here's my XY axis. VAN's got an angle 0, and VAN is almost always taken as the reference. So there we go. VBN lags the phase voltage for B lags the phase voltage for A by 120 degrees. So that's VBN. And then the phase voltage for C leads the phase voltage for A by 120 degrees. So that's VCN. The magnitudes or the lengths of all three of those arrows should be about the same. We see that VAB leads VAN by 30 degrees and slightly bigger. So that's going to look something like that. That's VAB, and that angle right there is 30 degrees. VBC is straight down in this direction. It's got a total angle of negative 90. And then finally we've got VCA, which is 207 angle 150. So that's about right there. And so we'll notice there's a 30-degree phase shift between those two, 30 degrees here and 30 degrees here. And there's three sets of voltages that are 120 degrees out of phase. It's 120 from AN to CN and 120 from AN to BN. It's 120 from AB to CA, and it's 120 from AB to BC here. So that's the phasor diagram for the voltages there. We were then asked to determine the currents. We were told that the line current in phase A, or sorry, the phase current in A is 10 angle negative 20. So IA phase is equal to 10 at angle negative 20 degrees amps. And from the diagram, you can tell that the phase current, the current flowing here, has got to be the same as the current in the line. So I phase A and I line A, those have to be the same. So we just have to find IA, IB, and IC. And in a balanced system, the currents are 120 degrees out of phase with one another, just like the voltages are. So IB is going to be IA times 1 at angle negative 120 degrees, and IC is going to be IA 1 angle 120 degrees. So that's going to be 10 angle negative 20 times 1 angle negative 120, which is just 10 amps at angle negative 140 degrees. And this one's going to be 10 at angle negative 20 times 1 at angle 120. So that's going to give me 10 amps at 100 degrees. So just quickly to summarize, for a Y generator, there are 4 voltages: VAN, VBN, and VCN. Those are called the phase voltages. VAB, VBC, and VCA are called the line voltages. And then there's 3 currents, and the currents are just labeled with whatever the phase is. So IA, B, IC.